In the previous videos, we have been looking at some major similarities between gravitation and electromagnetism, whose sources are mass and charge, respectively. We have examined these similarities from the two branches of modern physics, which are quantum physics and relativity. In the domain of quantum physics, we were able to produce for masses all the quantum mechanical equations which you have been taught only exist for charges. These equations include the momentum and energy quantization equations, the de Broglie equation, the Schrödinger equation, and so on. All the videos on that can be found under the Quantum Gravity playlist. Click on the channel profile below to go to my YouTube page and then select Playlist. Under Playlist, select the Quantum Gravity playlist, or you can wait till the end of this video and the link will pop up where you can just click on it. In the domain of relativity, we saw how charge can curve space-time just like mass, and Einstein's field equation for this was the same as that for mass. You can find the videos on that under the relativity playlist. In the last video titled How We Can Have Only One Fundamental Force in the Universe, I stated that there is only one fundamental force in the universe, which is gravity or electromagnetism. And I went further to show that they are the same. The obvious questions that come to mind immediately are: is there positive gravity? How can magnetism be included in gravity? Can we have EM waves from gravitation? This new series is designed to answer all these questions and work out clear explanations for gravitomagnetism. The backbone of electrodynamics is Maxwell's equations, and since I am claiming that electromagnetism and gravitation are the same, I will be deriving the Maxwell's equations for masses, starting with Gauss's law in this video. Don't forget to subscribe if you are new, and turn on the notification so that you can be able to watch all the episodes of this series. If you liked the video, please give it a thumbs up. When you place a charged sphere in space, or any kind of charge, there are field lines that spread from it outwards or inwards. These field lines are called electric field lines, and when the field lines are flowing away from the charged body, then we say that that body is a source. And when the field lines are flowing into the body, we say that that body is a sink. Now, let's bring a rectangular surface close to a charged particle. The number of field lines that will go through this surface is called the flux. And since we are dealing with electric fields, this flux is called the electric flux. So basically, an electric flux is the amount of field lines going through a given surface at a given time. Same thing happens with masses. A body of mass in space has field lines propagating from it. These field lines are called gravitational field lines. Again, when you bring a surface close to the mass, the amount of field lines that go through that surface is called the gravitational flux, which is identical to electric flux. We generally represent flux in physics with the Greek letter phi, and add a subscript to indicate the kind of flux we are dealing with. For this setup, let's draw the normal of the plane like so. To make an angle theta with a gravitational field line G going through the surface. We can resolve this field line into its vertical and horizontal components like so. We see that the component G sine theta does not go out of the surface, but rather flows in the surface. So you see that the actual amount of the gravitational field that goes out of the surface is the component g cos theta. So the flux through this surface, A, is equal to Aj cos theta. If you remember from vector calculus, the dot product between two vectors A and B is equal to the product of their magnitude times the cosine of the angle between them. This means that the gravitational flux is equal to the dot product of the area and the gravitational field. Let's consider a point mass m enclosed by a sphere of radius r. What is the flux through a small portion of this surface? The flux phi is equal to g dot dA. What we really want to know is the total flux through the entire surface of the sphere. To get that, we have to integrate over the whole surface. This is called surface integral. Subbing in the expression for gravitational field yields this. We can take out gm over r squared from the integral since the integrand is area. So we get this. This closed area is just the area of the sphere, which is 4 pi radius squared. Therefore, the total gravitational flux through a closed area is equal to 4 pi g times the mass enclosed. This is true for any kind of closed surface, not just spherical ones. For electric fields, we have what we call permittivity of medium, epsilon, which is a measure of how much medium impedes the flow of the electric field lines. This is related to the Coulomb's constant as follows. I can also write the gravitational constant G as this and call epsilon bar the gravitational permittivity. This doesn't change anything about gravitation. We have simply written G in terms of another constant. By expressing G in this way, we have flux equal to this, which is equal to the mass enclosed divided by the gravitational permittivity. And this is Gauss's law of gravitation. We can write epsilon bar as 1 over 4 pi g. We know that g is equal to 6.6 exponential minus 11. So subbing it in here gives epsilon bar equal to 1.2 exponential 9 kilogram squared per meter squared per Newton. Take note of this constant, as you will later realize that it is a fundamental constant, and we shall be seeing it often in this series. There is a mathematical theorem called the Divergence Theorem. It states that the surface integral of a vector field f is equal to the integral of the gradient of that field over the volume enclosed by that surface. So, the gravitational flux phi, which is equal to the integral over a closed surface of the gravitational field, can also be equated to the integral of the gradient of the field over the volume enclosed. And this is also equal to the mass enclosed over epsilon bar. The mass enclosed can be written in terms of mass density ρ as follows. Therefore, we have this volume integral equal to the integral of ρ over epsilon bar dV. For these equations to be true, the divergence of G must be equal to ρ over epsilon bar. I am sure you are also familiar with this other form of Gauss's law. It is the first of the 4 Maxwell's equations in differential form. In the next video, we will derive the second Maxwell's equation for gravity, which is where we will introduce the concept of magnetism due to gravity. Subscribe if you want to be notified when the next video is uploaded. and don't forget to give the video a thumbs up. See you in the next video.